Okay. So as I told you, your wireless communication will have four questions. Okay, four questions. Okay, and each for one question you will be given 45 minutes. 45 minutes. That means it will be a 3-hour paper. Okay, 3-hour paper. Okay, so you will be having four questions. One question, first question one related with path loss model. Okay, path loss model. The second one is related with statical multipath channel, statical multipath channel, multipath fading channel, multipath channel, most probably relay channel. Okay, more weightage will be given relay distribution, relay channel. Okay, relay channel. So you need to study the relay channel. Okay, the Raisian and Nakagami no need actually. Okay, so you can only care in about this relay channel. Okay, question three is related with mm, diversity, diversity techniques. Okay, diversity techniques. So actually diversity technique combining, diversity combining techniques are given. Okay, combining techniques. Okay, so maybe you can remember that MRC equal gain combining and selection combining. Okay, so these three combining techniques we have seen. Okay, and more weightage will be given MRC and equal gain combining. Okay, so diversity combining techniques. The fourth question is related with MIMO. Okay, first question is related with MIMO. So you will be given a matrix. Okay, MIMO matrix. Okay, for it may be 3 by 4 or maybe 3 by 3 matrix. Okay, and you will be asked to find the SVD. We have already done this. Okay, so I'm not going to do any example related with question 4. Okay, so learn how to find the SVD. We have done 2 questions, I think, as I can remember. Okay, so maybe in chat GPT also, if you find if you type just find the SVD for 3 by 4 matrix, you with all step or something, then it will give the solved example. Okay, then you can refresh your mind, refresh your memory. Okay, how to solve how to find the SVD of a matrix. Okay, so most probably it will be 3 by 4 or 3 by 3 matrix. Okay, an easy one. Okay, so those are the 4 questions you will be having. Okay, so actually I'm not going to do any questions here, but I will ask you to do some question, all the questions. Okay, all the so uh, so most of the questions we have already done in classrooms. Okay, so I will again show you, just do that questions. If you have any problem, just ask me. Okay, so first we will go to path loss model. Okay, so this is the path loss model, 24th. Okay, so path loss model. Okay, okay, you can you just see what are the large scale propagation effect and small scale propagation effect. Okay, maybe you can remember. Large scale means that that distortions or variation, signal variation occur uh, in large distance, in large scale propagation. Okay, but in small scale propagation, variation of signals will happen in small distance also. Okay, for example, large scale propagation effect happen due to path loss and shadowing. Okay, so these are relatively large distances. Okay, but the small scale propagation, the multipath propagation, multipath effect. Okay, so that is happen uh, in short distances. Okay, so just learn large scale propagation effect and small scale propagation effect. Okay, and you need to be able to compare, or maybe if you ask any question, so you need to, it is just a theory thing. Okay, so you, only you need to know these things. Okay, large scale propagation effect and small scale propagation effect. Okay, and also maybe you also should know the wide band and narrow band. Okay, narrow band, maybe you can remember that. Okay, if the bandwidth is if the bandwidth of a system, bandwidth of the system is greater than the coherence bandwidth, we called it wide band system. And if the bandwidth is less than the coherence bandwidth, it is a narrow band systems. Okay, just learn what is the coherence bandwidth and coherence time. I think we have already done those things. Okay, so that is the wide band and narrow band, and also the wide band. Uh, if you consider the wideband, it will support high data rate because it has a higher bandwidth. Okay, but narrow band is good for low data rate application. Okay, because its bandwidth is less. Okay, uh, uh, so that kind of informations may be there. Okay, so uh, just learn wideband and narrow band systems. Okay. So large scale propagation effect is called propagation effect, and also wideband and narrow bands. Okay, and here you can see. Okay, so this is the distance that is actually log. Uh, uh, the log scale is considered for the distance. Okay, because this is the distance will be very high. It may be 0 to 1,000 kilometer, 100 kilometer. So you need to small that is scale. Okay, so that is why you use log uh, distance. Okay, log scale distance. Okay, so this is the uh, gain of the channel. Okay, so you can see that the gain is changing due to path loss and shadowing. It is somewhat slowly happening. Okay, slowly happening, but due to multipath, it is quickly happening. Okay, so you can see this here. Okay, uh, okay, then you need to refresh your memory on path loss model, especially free space path loss model. So so maybe this kind of questions you will have, so very easy. Okay, so for example, just do this example. What you need to do is you need to substitute all this value to this one. Okay, so here the frequency is given. Using frequency, you can calculate the lambda using V equal F lambda. Okay, so V is the velocity of light, that is 3 by 2 to the power 8 meter per second. Okay, so you can use this value and you can calculate lambda if F is given. Okay, so you can substitute the lambda here. Okay, and so it is non-directional antenna. If the non-directional antenna, if it is a non-directional antenna, normally this GL is referred as 1. Okay, is assumed as 1. So you can apply that value also. Okay, uh, so your transmit power should be around. So at the receiver, you at least you should have around 10 microwatt. okay, 10 microwatt power to decode the signal very well. So to have this 10 microwatt, you are asking to find the transmit power. Okay, so this is the transmit power and this is 10 microwatt. Then the distance also should be given this, that is the 100 meter. So you can apply those value and you can find the transmit power. Okay. Hello. May Okay. So so it is not much difficult. Okay, so you have to apply the value. Okay, so this kind of question you will have. Okay, so it is maybe around 6 marks. Okay, so easily you can get marks. Okay, so the exam maybe not fast. Okay, so sometimes this is maybe given in dBm. Okay, so if you are given the uh, uh, given this receive or power using dBm. If you are using this equation, you need to convert this dBm into watt. Okay, so dBm means if you have a milliwatt value, if you put 10 log 10, okay, 10 log 10, so you will be having the dBm. Okay, so you need to get the inverse value. Okay, 10 to the power. So dBm value you can divide it by 10, then you can get 10 to the power this value. Okay, so you will be having the milliwatt value. Then you can apply it here and find. Okay. Uh, or else if these are given in dB, so this you can also use this one. No, this is also be given in dB. Okay, so maybe you can use maybe this one. Okay, so this equation you can use, or maybe you can convert it to what, that you can apply it here. Okay, so any approach will be accepted. Okay. So you will so try to do this one, that is very easy. And also you will be having one question related to Rayleigh distribution. Okay, most probably with two-ray model. Okay, two-ray model. Okay, for the two-ray model, actually, so this is the equation for the two-ray model. Okay, two-ray model. Uh, Okay, so this is the receiving power is approximately equal to this one or this one. Okay, so you can use this one or this one, no problem. Okay, so if you are given frequency also, maybe you can use this one. And if the frequency is not given, maybe you can use this equation. Okay. So this one or this one, these are approximately equal. Okay. So you can use either uh, approach. Okay. Either approach, either equal. Actually, this one, this one is after simplify this one is getting, no? So you can use this one actually. Here also the frequency and frequency will cancel. Okay. And hatara 4545 will cancel. So this is the final value. Okay. So you can use this one. Okay. You can use this equation. Okay. This equation. So if you are given, okay. And also just see this. So, okay. For example, you can see that, okay. If it is two ray, okay, if it is two ray, so one signal, the direct signal will come quickly, and the reflected signal will reach after that. Okay, so if this signals come time is T1 and this signal come time is T2, received time is T2, T2 minus T1 is the delay spread. No, this is the delay spread. This is the delay spread of this two signal. Okay, so maybe you will be asking to find the delay spread. Okay, so you need to calculate this. So maybe you are given this distance. If the distance is given, uh, so you know the traveling velocity, that is the light velocity, then you can calculate t. Okay, then you can find the delay spread. Okay, so and if this path if these paths are not given, okay, again you can find the delay spread. There is a approximated approximated equation. This I can remember. This DC is referred as critical distance. Okay, critical distance. Okay, actually, you know that, okay, if the signal delay is all the directly related with the phase, no? If for example, if this is the receiver, okay, if one signal is received here first and next signal is received after that, that means there is a phase difference between this signal and the later signal. Okay, so the phase difference, that is if it is delta phi, okay, so this is directly related with the delay. Okay, this is directly related with the delay. Okay, so okay, so you can read this. Okay, delay spread of two-ray module between a lowest path. Okay, so this is what I told you. Okay, then okay, so this is the delay spread. You can see that this is the delay spread, and this is the phase difference of two signal. Okay, so you can see that the same values are there. Okay, so see that is V here, and 2, 5, C equal to F lambda. Okay, C equal to F lambda. So instead of this C, you have lambda here, and also there is a 2, 5. Okay, so you can find the relationship between this delay spread and delta 5. Okay, delta 5. So you can find the delta 5 here. Okay, you can find the delta 5 here, and using delta 5, if you know this value, okay, so you can find, I think you can find this one. Okay, so it is clear, no? It is not much difficult. I think you can do this, okay, by yourself. Okay. So, so if you are asked to find the delay spread, and if you are given the distances, no problem, you can find using this C. If you are not given the distances, actually you need to have, so you need to have this frequency and also this the receiving and transmitting antenna height. Then using that one, you can find the uh, phase difference, delta 5. Then you can find, so if you find the delta 5, then you can find this value. Okay. So using this delta 5, you can find uh, uh, this one, this x plus x dash minus L divided by C, you can find. Okay. So that you can find the delay spread. Okay. So, so I hope you get it. Okay. And also just tell me what happened if this signals, so sometime in two-way signal, if you have a two-way signal, sometime this receiver signal can be zero. Is it possible or not? Just tell me. Can this receiver power will be zero? If it is a two part, can this be zero? Can this receiver power will zero? Can this receiver power zero? මේ receiver power එක බිඳුවක් වෙන්න පුළුවන් කවදාවත්? Just tell me. මෙතන බිඳුවක් වෙන්න පුළුවන්ද power එක? Can this received power will be zero? Hmm?